So we have satellites moving in an orbit, and they have radar, sensor, radar, transmitter. They send signal, radar signal to the sea, and they get the reflection. That's the principle. The signal comes down to the sea and they come back. And based on this, the speed of the radar signal and also the travel time from satellite up to the sea level, we can determine the height of the satellite over sea. So, but what is the point for that? If we want to measure the satellite altitude, we need the reference surface, a reference ellipsoid, and we can compute the height of the satellite with respect to the reference ellipsoid. So if we have the height of the satellite with respect to reference ellipsoid, and also how can we do that? We have precise orbit. Orbit is clear. Orbit is computed precisely, and also based on this orbit, and we know the geometry of ellipsoid. Based on the coordinates of the satellite and geometry of ellipsoid, we can determine this height of the satellite. For example, let me draw something like a figure here. If I have a satellite here, and I can determine its position, let's say X, Y, Z, from the center. Then I can determine the height or distance between the center of the Earth and the satellite. So if I can do that, then I can have the distance from the satellite up to the center of the Earth. The rest is to compute this side, this part. So if we assume that the Earth is spherical, it will be R. That's simple. Even if it is not a sphere and it is still ellipsoid, it is also simple to compute this based on the latitude of the satellite. So the geometry of the ellipsoid is clear for us. We know it. And we determine the satellite coordinates by methods, different methods. We can use gravity models to compute satellite. We can have some GNSS receiver on satellites to measure, or we can have some reflectors on satellites and determine the satellite orbit using laser lunging, different methods. But we assume that the orbit of the satellite is known. The coordinate of the satellite is known. When the orbit is known, the coordinate, the distance from the satellite to the center of the Earth is known. So that we have this distance. And based on the geometry of ellipsoid, this is easy to find how far the ellipsoid is from, how far is the satellite from ellipsoid. That's clear. So I can simply say that the geodetic height, geodetic means height from ellipsoid, is known. Based on the geometry of the ellipsoid and determining it from and subtracting it from the distance of satellite from the Earth center, we can determine the geodetic height. That's known. That's the first assumption. And what do we measure? We measure the distance from satellite up to sea level. There's something is missing here. You see here. Something is missing because we do not have height of the satellite from the height of the sea from the ellipsoid. Then what can we do with it? So I say, okay, the distance from the satellite or the geodetic height. Let me show it by H. H of satellite is known. Okay, so let me call this part SSH, which is sea surface height. So I can SSH. What remains here is actually what we measure. This is a measurement. So the altimeter measurement, which is the distance from the altimeter transmitter to the sea level. It means that we measure the sea surface from the orbit. But you know that the orbit of the satellite is perturbed by different forces, and it's not constant. It's not. Then it is. It means that it's going up and down. So if I want to get want to determine the distance from the satellite to sea surface, it is possible with the measurements that we have. But we should consider that the changes of the orbit should be there as well. Let me consider that. So the distance between if I remove this and we come to the altimetric measurement, then I get it R. Or this is the measurement actually. So this is a simple formula for the measurements of altimeter data. H, geodetic height of a satellite, is now from the orbit. Sea surface height is the things that we don't know actually. We want it. And A is the measurement. So if I simplify this formula, so I will write SSH or SSH, sea surface height is the geodetic height of the satellite minus the measured distance between satellite and sea surface. That would be sea surface height. So sea surface height is actually a form of geodetic height from the bottom for the sea surface. So it's not that simple because we have an altimeter here and it transmitted the signal down to the sea. This signal passes through the atmosphere. We have ionosphere. Here can influence the signal, and down there we have troposphere. And for troposphere, well, it is also have a dry component, and also it has also a wet component. So water vapor is there, and usually these things are also influence the satellite the signal. It's similar to GNSS signal. The signal passes through the atmosphere. It will be influenced by the atmospheric particles. So that's normal. But these are the things that which are related to the distance between satellite and sea surface. But is sea surface constant? Not at all. So which type of movements do we have in sea surface? So for sea surface, what we have is tide. We have already discussed about tide, that when we have the earth and we have water in it and we have moon inside, and the gravitational attraction of the moon pulls the water, pulls the earth towards itself. And we have already discussed that at the other side we have high tide, and here we have low tide based on the direction of the moon. And it's not only tide, it's not only for water. We have solid tide. It means that even the mass of the earth is pulled towards moon. It means that because the earth has, we know that the earth has three layers: crust, mantle, and core. Mantle is viscous medium, is soft, and when the moon pulls this as to what is said, this will deform. This deformation is called solid tide. Also, we have ocean tide, which is very clear, the water movement. So it means that the places that the moon is above them, water will be at higher level there. Because so you see, the sea surface is not constant. We have to compute these effects. Also, we have polar tides. Polar tides. That these tides also will influence also the sea surface. Where is the position of based on the, it will involve with the position of pole and changes in the position of pole and also the Earth's rotation rate. So a lot of parameters that will influence the sea surface. And on top of these things, we have also magnetic field of the Earth, which can influence radar signal. So if I want to say error sources for altimetry. So these effects, these corrections are necessary for the satellite radar signals. Then they have to consider that, they have to compute this, how large these effects are and how much they affect this radar signal. They will correct the signal, and after that, they will correct the model the sea level variation tides, and then try to get it better than the sea surface is real, is not inside this. So then now I write this mathematical equation with a more complete form. Accessory satellite geodetic plus its all random errors, or the error of the orbits, which is also there, plus altimetry measurements. And we know the error of altimetry measurement has also their own limitations, random errors or other things regarding the sensor and also the transmitter. These errors are there, plus the corrections, let me say, a ionosphere correction, a troposphere, and it is dry component, plus a troposphere wet component, plus a magnetic field, plus a solid tide, plus a ocean tide, plus a, and this is polar tide. You see different types of corrections are needed to these altimetric measurements before we compute SSH. So these are corrections for us.